Welcome to everyone who is able to tune in to our next segment, Virtual Blue COP 25. And my name is Dwight Owens. I'm with Ocean Networks Canada in Victoria, BC. And I'm very happy to introduce our next speaker, who is Yassir Eddebbar. And he is a postdoctoral scholar at the Center for Climate Change and Impacts and Adaptation at the Scripps Institution of Oceanography. Yassir received his PhD in oceanography at Scripps, where he worked on understanding the coupling of the oceanic oxygen and carbon cycles to climate. Currently, as a member of the Integrative Oceanography Division, Yassir is focused on improving our understanding of how climate and ocean circulation impacts marine ecosystems, habitats, and the regional scale, with a particular focus on oxygen minimum zones. Yassir is also interested in communicating the central role of oceans to human livelihood, and frequently engages policymakers, teachers, and the general public on a variety of ocean and climate-related topics. So today we're very happy to have Yassir join us from San Diego and to introduce this very interesting and important topic. So now I'll turn it over to you, Yassir. And as you're speaking, I'll be monitoring questions that may come in. And so we'll leave a little bit of time at the end and I'll relay those questions to you as well. So please take it away and thank you very much, Yassir.
Sounds great. Thank you very much, Dwight, for having me. And hello to everyone across the globe for joining us. Thank you for joining us in this session and on Oceans Day at the virtual Blue COP 25 and at Blue COP 25 in Madrid. My name is Yassir Eddebbar, and I'm gonna share my slides here so that I can share some. See. So I can share some of what I was going to talk about today. So I work with the Center for Climate Change Impacts and Adaptation, where I am a postdoctoral scholar at the Scripps Institution of Oceanography. The topic that I want to talk today about is essentially observing how we observe climate change from global to local scales. And me 1 second. I just want to remove the chat box and off we go. Okay, so the topic today is observing climate change from global to local scales, and really how to relate it to mitigation and impacts and adaptation. Before I get started, I really want to thank the organizing committee for virtual Blue COP, specifically Luisa Sarmiento, Soren Thompson, Axel Bertrand, and Bluen Guiu, for organizing a virtual Blue COP that allows people to share their expertise and knowledge across the world, and without having to fly to COP, and in the process reducing their carbon emissions. And I truly, truly hope that the Conference of the Parties COP in the future starts to use this kind of virtual platform to exchange information as opposed to having everyone fly to the same meeting. I think it's really important to have more of these virtual meetings as a mode of communication as well, more as a complementary mode. So kudos to the team for organizing this great platform. So before I get started, I wanted to put the observational efforts in the context of the UN Framework Convention on Climate Change, so the policy process that is benefiting from these observations. Specifically, the COP process, which started somewhere around 1992 when the United Nations Framework Convention on Climate Change was created. And it took several COPs, about 25 or 26, but there are also mid-year COPs where a lot of the information from the different COPs are being processed. And I want to show some of the important meetings, for example, the 1997 Kyoto Protocol, when it was ratified and led to the Kyoto Protocol being the governing policy framework for climate change. But it wasn't really till the second half of the 2000s when we started really taking climate change mitigation and adaptation into the policy process. And that started with a series of really important conference to Paris, starting with Bali, Copenhagen, and that culminated into what we know today as the Paris Climate Treaty of 2015. So since 2015, the global community came together and decided that we have to act on this treaty, and that included nations essentially coming up with their climate action plans or nationally determined contributions on how they're gonna implement the Paris Climate Treaty, how they're gonna observe, monitor, adapt to climate change, and what kind of mitigation and adaptation strategies they need to put forward. And so as the Paris Treaty is gonna go into effect next year, the last few COPs have really focused on how do we do this in a concrete way. And that's why I think COP25, Chile, which is now held in Madrid, is really important. It's because it's gonna lay out the concrete steps for each country about how they're gonna mitigate climate change at the national level, but also how they're gonna adapt to the impacts of climate change. That includes observing how climate change is evolving at the national level and regional level. And so perhaps one of the most important observational records for understanding the role of humans in impacting the climate system is the carbon dioxide concentrations in the atmosphere, CO2 measurements that were started at the Scripps Institution of Oceanography, from where I am reaching you today from. And what you see here is a picture from the last COP meeting in Bonn, and this is the SUBSTA meeting that was held in June of this year. And what you see to the left is the Keeling curve, the CO2 measurements in the atmosphere, going up with a reading of about 414.71 parts per million. This measurement is extremely important to the global community meeting today at COP25 in Madrid, because it allows us to understand how much progress we've made, how many emissions, how much our emission reductions has actually impacted the amount of CO2 in the atmosphere. But in addition to that, it tells us how the natural carbon sinks are also reacting. So in the plot to the left, what we see is in the upper panel, the amount of fossil fuel and cement carbon fluxes emitted to the atmosphere, the amount of carbon dioxide flux due to land use changes in brown. And on the other side, what we see is where that carbon dioxide eventually ends up. And so about 50% of that carbon dioxide ends up in the atmosphere, accumulates in the atmosphere. The other 50% is taken up by land and ocean natural carbon sinks. And that can occur through enhanced photosynthesis on land, or for the ocean through the carbonate chemistry of the ocean by absorbing CO2 at various depths. So that's why it's really important to measure CO2, and that's why it's really important to keep track of how much CO2 accumulates in the atmosphere. And I've plotted here to the left the CO2, I'm showing here the CO2 Keeling curve, but also the locations where carbon dioxide is measured across the globe. And that's being done currently both by the Scripps CO2 program and also by the NOAA program. And a really important reason for measuring carbon dioxide is to understand the amount, how the energy imbalance in the atmosphere relates to the radiative forcing that is caused by carbon dioxide and other greenhouse gases. So what you see on the right is the planetary energy imbalance, essentially the amount of energy trapped in the climate system. This is from the 5th IPCC assessment report. And you could see the energy trapped by different components of the climate system. So in light blue and dark blue is the amount of heat trapped by the ocean. And then you see the fractions taken up by ice, land, and atmosphere as well. And they're pretty small compared to how much heat is taken up by the ocean. So we know that the heat trapped in the Earth system is essentially being primarily taken up by the ocean. And what you also see is that the uncertainty around how much heat is stored in the climate system has drastically decreased since 2000. And that's primarily thanks to the Argo Float program. So the Argo Float program is a global international program made of over 30 different countries and is essentially a network of Argo floats. These are floats that you see, for example, an example of that is on the left, that go up and down in the ocean, the upper 2,000 meters of the ocean, and sample the temperature and salinity of the ocean. That tells us essentially how much temperature change is occurring over time, and it also is telling us about the spatial pattern of warming in the deeper ocean. This is really hard to measure with ships alone or other methods. So it's really given us a critical view of how much heat is being stored in our system, and especially specifically in the ocean. This beautiful map shows the contribution of different countries to Argo Float deployments, and you see a substantial amount of these floats are done by the United States, but also various other countries are now contributing. And the hope is that this program will be continued for the next 100 years, that all countries contribute to this really important monitoring, global monitoring network. So how does Argo work, or an Argo float works? So a float would come up, is at the surface, where it typically can transmit data to a satellite. It descends to about 1,000 decibel or 1,000 meter depth. And then it drifts for about 9 days along that 1,000 meter depth. And then it descends another 1,000 meters all the way down to 2,000 meters. And then slowly it goes up to the surface, and on its way to the surface, it measures temperature and salinity and relays that information back through satellite to a data center where it is processed and is essentially more or less given live to the community to use in research and in monitoring. And what do we learn from Argo? We learn, for example, that the ocean has continued to take up heat, even though over the last couple decades, even though global mean surface temperature may have flattened for a little bit, for about 15 years. So that was an important contribution of Argo to show how much heat is being stored even during the hiatus in global mean surface temperature. It also gives us a really clear idea of the structure of warming, both in the vertical and in the horizontal space. So you could see in the right here in a paper by Dean Remick and colleagues, you see that the ocean heat content has been increasing, both in the upper 500 meters, but also at depth between 500 and 2,000 meters. And there's some variability on interannual timescales. And you could also see the trends in in space. And you see that certain areas are warming faster than other areas. And that reflects both physical processes that drive ocean heat storage, as well as the imbalance of essentially of heating across these different spaces. So it's really important to keep track of how warming actually is occurring in these different regions, especially when we're thinking about coral reef ecosystems and small island nations that are seeing some of the highest warming rates here on this map. So the future of Argo is moving at deeper depth. To the right, I'm showing a map of the lines that are crossed by ship observations that have been measuring ocean warming at depth below 2,000 meters. And there's a great paper by Sarah Perkey and Greg Johnson, 2010, that laid out how much warming we've observed from these ship line observations. But the goal in the future is to try to really monitor ocean warming with little spatial gaps as well as temporal gaps. And that's something that the Deep Argo Float program is going to really be helpful with. So new Argo floats will be able to go below 2,000 meters all the way down to 6,000 meters and measure temperature and salinity, and they will be able to give us a really critical insight into changes in both the ocean heat content, contribution to sea level rise, as well as the freshwater budget of the ocean. And you could see in this new map here, and if you'd like more information on this program, you should visit argo.ucsd.edu. You could see some of the pilot programs for some of these new floats that are being deployed and are successfully making these new measurements at depth. So this is an absolutely exciting new program that is really making some important headways in terms of how we are understanding how the heat budget of the heat content of the ocean is changing over time. And if you are at COP25 in Madrid, you should definitely stop by the Scripps booth. This is booth number 30, where we actually have a prototype of a deep Argo float at our booth. And you see to the left our exciting team of scientists presenting some of the instruments and some of the work that we're doing here at Scripps. And to the right bottom, you see our director, Margaret Leinen, talking to Nancy Pelosi, Speaker of the House, about the uses and importance of these programs in measuring how much warming is happening globally. So it's really an exciting time to reach out to the policy maker community and have them involved in our expansion of how we're monitoring the planetary system at large. In addition to sampling the deep ocean, I think a major new way for measuring how the ocean is changing that Argo is starting to contribute to is the Biochemical Argo Float program. So these are Argo floats that are equipped both with temperature and salinity sensors, but also with oxygen, nitrate, pH sensors that are allowing us to measure other aspects of the ocean. For example, ecosystem drivers, the amount of oxygen at depth, the amount of nutrients, and the acidity of water. And to the left, you see a map of the current live biochemical Argo floats. And a lot of these are being deployed or have been deployed in the past few years in the Southern Ocean. And they're giving us an incredible insight into the carbon cycle in the Southern Ocean, and also the oxygen distributions. And the major goal moving forward will really be deploying more biochemical Argo floats in other areas where we don't measure oxygen and nutrients and pH at enough spatial and temporal resolution. So the tropical Pacific is especially a major opportunity here, where some of the lowest oxygen levels are occurring naturally and where some of the oxygen minimum zones have been observed to expand. So a key role for biochemical Argo floats here is going to be understanding what are the mechanisms governing oxygen minimum zone expansion, and also the amount of carbon that the tropical Pacific modulates, as well as nutrient transport and how productivity changes in this region. So there's a lot of new and important insights that might come out of biochemical Argo into the future. And one way to do this is currently the tau array, which is how we measure a variety of physical and biochemical properties in this region, is currently being reinvented. And so biochemical Argo might be helpful in and improving the observational capabilities of this program. And if you're interested, you should look at the Tropical Pacific Observing System website, TPOS 2020, where they're detailing some of these potentially new additions to this region. So what is the importance of some of these global observations? One of the most important uses is informing our current model projections of marine ecosystem drivers. For example, sea surface temperature change, pH change, oxygen at depth, and primary productivity. These are plots from the IPCC report, from a paper by Bob and colleagues, that show by the 2100, we know that sea surface temperatures will warm with enough certainty, and the stipplings indicate where the models agree. We also know that the ocean will become more acidic into the future, and we know that the oxygen content of the ocean will decrease in a warmer climate. And productivity also shows in purple here some decreases as well as some increases in certain regions. The stipplings for oxygen and productivity shows that there is disagreement between models in certain regions like the tropical Pacific and the Southern Pacific and tropical Pacific and North Pacific for net primary productivity. And that's really important because these models are not able to resolve some important processes that happen at these at the scales that are important at these regions. For example, mesoscale eddies and equatorial undercurrents are not very well represented in this region, and so different models might not represent how these processes might be impacting oxygen and productivity change into the future. This is especially important for oxygen, where the most recent synthesis of oxygen observations have shown that there is a pretty well observed global decrease in oxygen content, and there's some high decline rates in the tropical Pacific, whereas the models don't really show similar decreases in the oxygen content in this region. So there's currently a sort of a discrepancy between the models and observations, and that's something that the biogeochemical Argo Floats will really be helpful in informing the models whether they're representing those processes very well. And another advance that's going to really help us understand how marine ecosystems are going to be changing to the future is an increase in model resolution. So the former IPCC type models typically have about 1 degree by 1 degree resolution. And now models are increasing in resolution. So now some of the modeling centers are able to resolve scales down to about 1/10 of a degree. Although this still remains very computationally expensive. And here I'm showing a test model simulation of dissolved oxygen at 200 meters. And we can see the importance of some of the mesoscale processes like eddies that are increasingly being observed to be important for oxygen minimum zones. For example, off the coast of Peru and Chile, off the coast of California, along the equatorial Pacific, in the Indian Ocean and the Atlantic Ocean. So as models begin to improve their resolution and their computational efficiency, our understanding of these impacts is going to improve. And over the next 10 years, with the decade for ocean sciences, I think an important contribution to the policymakers community and to adaptation in general is to use our newly gained information and knowledge about regional scale changes to inform adaptation plans at the local scales. And a topic that I'm really interested in are small island nations in the tropical Pacific that are heavily reliant on marine ecosystem resources. And I think over the next 10 to 20 years, marine adaptation plans will really benefit from both the new observations that we'll begin to make from gaining information from biogeochemical Argo Floats, as well as from higher model resolution. And that's going to be both a major challenge and also a major contribution to our understanding about how climate change evolves in the ocean. And then finally, I wanted to end at the local scale. So we moved from atmospheric CO2 at global scales, and now we're moving down to local scales. And this is an effort that is led by the center that I work in, the Center for Climate Change Impacts and Adaptation. You can visit our website at climateadapt.ucsd.edu. And this is a pilot program called Resilient Future, and it's focused, it's a wave and sea level observing network, and it's focused on deploying observations and improving models of forecasts of sea level change, both due to changes in tide, waves, and also long-term sea level rise. And the main goal is to develop site-specific predictions for some of the high water events that we see, for example, in winter, when we have very large swell events here in California that might be combined with king tides, for example, as well as the long-term change in sea level, and try to inform the policy community, for example, the flooding prevention programs in different cities about any upcoming flooding risks. And a couple examples here, I'm showing a map of the city of San Diego, where we're focusing on at the moment. One is the city of Imperial Beach, where we have a series of sensors, wave buoys, pressure sensors, tide gauges, and these are coupled with models that allow us to, models of wave run-up that allow us to give the community a heads up within enough time on whether a flooding event might be occurring. And to the left is a picture of the total water level, or a plot of total water level during January 18, 2019, and a picture of some of the flooding events that have occurred during that time. And this is really stresses the importance of observations and process understanding of the impacts that we are seeing at the regional scales. And it really highlights the importance of both using observations at the regional scale and global scale. And also, we're hoping to use this model as a pilot or an example to scale up our efforts globally to reach out to communities that do not have these resources. And an important component of this is community engagement. So we host the community from San Diego, across San Diego and the state, to these climate summits, where we present on some of the latest climate research, but also hear from the policy community about their needs and their efforts, so that the scientific community and the policymaker community are on the same page. So with that, I want to close with the same first plot, the first timeline that I showed on where we are today. So the 2015 Paris Treaty should be going into effect in the next year. And I think an important path forward is really how we're going to adapt to the impacts of climate change, and also understanding the impacts themselves, because they're extremely important in informing how much we have to mitigate and the importance of mitigation, especially with certain climate change impacts that are not avoidable. And COP25 in Chile is really ideal to get both the community, the policymaker community, and the scientific community together to try to hash out some of these details, and especially as the various nations and parties are submitting their nationally determined contributions, their updated climate action plans. It's important that they really start getting concrete about how we're going to observe the impacts and how we're going to adapt to them. And that's going to require a lot of work moving forward, and a lot of interaction with the scientific community on both ends. And with that, I encourage you to visit our website and the Scripps website. And I'd like to give the floor back to you, Dwight.
All right, thank you very much, Yassir. That was really interesting. And I know here at Ocean Networks Canada, we are very interested in Argo. And we're hoping to get some Argo floats and increase our resolution of studies in the Northeast Pacific. We've been focused a lot on very high resolution measurements from cabled observatories. So it's high resolution at a limited number of points, and the Argo can really help fill in some of the blanks there. But I noticed when we were looking at those maps of Argo coverage around the world that there's a big area that's blank, which is the Arctic. And so how can we, is there a way to do Argo in the Arctic, or how do we know about changes in the water column in that part of the world?
That's an excellent question, Dwight. And I think you touched on a really important point, is that Argo both has an impressive reach in the global oceans, but it also has limitations. And one of the long-standing limitations has been ice-covered regions. However, actually there is now technology that allows Argo floats that go beneath sea ice and measure ice and relay that information back to the satellites through specific methods that I encourage you to go and see the Argo program website itself. I don't want to give you the wrong information.
Sounds complicated.
But yes, but the technology now exists, and it's being deployed in the Southern Ocean around Antarctica. And it shows just the importance of scientific innovation in resolving some of these issues. And I think over the next couple decades, I think the technology is going to improve that where we'll be able to observe more of the Arctic more easily.
Oh yeah. Let's see. Oh, I had another question about the bioargos, and you mentioned the different sensors on there. One of them is pH, and from my understanding, pH is really challenging, and the sensors tend to drift or need a lot of recalibration. So can you tell us anything about how that challenge is addressed?
For pH, I think a major solution for addressing some of the calibration issues, some of the calibration issues also occurred with the oxygen sensors earlier on in the 2000s. A lot of these, for example, for oxygen, some of the calibration issues have been resolved, and there's several papers that have detailed how to resolve some of those issues. An important point to make here is that biochemical Argo is really important to be complemented with ship observations that will give us in situ high precision measurements that give us confidence in the pH measurements. So it's important to make these two observations at the same time, especially routing some of those autonomous float observations with in situ observations from ships, so that we can actually understand the magnitude of the drift, and also and just have independent observations of these different systems in general.
Oh yeah.
So the importance of ship observations cannot be more highlighted. It's extremely important to maintain the ship observations that we've been making over the last 6 decades to make sure that we're still getting the full coverage, and especially some measurements that are not made possible by Argo floats.
I see. Yeah, I know that for our region, we've been talking about getting Argo floats and sort of babysitting them, tracking them, and then when they get too far away, go get them and bring them back to put them back into our footprint. And I guess those would be the times to do the in situ measurements.
Yes, absolutely. Yeah.
Now, you showed a map of Argos or the lack of data in the equatorial region, and why is that?
At the moment, biochemical Argo is a new program. and there was a strong focus on the Southern Ocean over the last 5 years or so. So you could see in that map that there's a lot more biogeochemical Argo floats in the Southern Ocean. It was really to try to gain a deeper understanding of the carbon cycle and biogeochemistry around the Southern Ocean, which is really important for the global carbon cycle. The Southern Ocean is one of the major carbon sinks in the world's ocean. And these biogeochemical Argo floats are now giving us really unprecedented temporal and spatial coverage of the carbon distribution. And this requires some workaround because most of the floats have pH sensors. There's not enough DIC measurements out there yet, but they're really giving us a new insight into the biogeochemistry of the Southern Ocean, and that was a main priority.
Mm-hmm.
I think moving forward, the next priority is going to be moving globally and try to cover certain regions that are important as well for the global carbon cycle, but also for other biogeochemical cycles like oxygen, which is a problem that I work on. The tropical Pacific contains some of the world's largest oxygen minimum zones. And these oxygen minimum zones have been observed to expand in the last decades. Mm-hmm. And a mechanistic understanding of how the oxygen minimum zones are expanding is still not clear. And that's going to require more observations. The observational coverage in tropical Pacific is still pretty sparse. And so over the next 10 to 20 years, it's really important that we gain enough of an observational coverage of how the oxygen minimum zones are structured, what are the drivers of, for example, mesoscale processes like eddies and the equatorial jets, and just as importantly, what do the models themselves, how do the models represent these oxygen minimum zones, and how can we improve these model representation? That's going to require both the use of observations and model simulations at the same time. I think we've got a lot of opportunities in that region, and I think it's extremely important to the Pacific community in general. Peru, Chile, who is hosting this COP this year, is heavily dependent on marine fisheries. It's a very skinny country that is essentially fully dependent on the ocean. And it also borders one of the largest oxygen minimum zones. And Soren Thompson, who's one of the organizers of Virtual Blue COP 25, is an expert on how some of these mesoscale and submesoscale processes, these fronts, influence the oxygen minimum zones in that region. He's worked on some really important work that shows that it's important to understand these processes at these small scales. And biogeochemical Argo floats, gliders, and improvement in model resolution is really the best way moving forward in addressing that problem.
Oh yeah. Great. I would like to ask more questions about that, but we have some questions that have come in from our audience. So I guess this first question is related to my question. Do you have any ongoing expeditions at sea at the moment in the north? So maybe not in the Arctic, but in the northern regions.
Myself, no. I work primarily with models. So my expeditions are primarily in the office and on servers. However, there are absolutely expeditions that Scripps is taking. In the Arctic, there's been expeditions recently. If you visit our website, there's more details on some of the expeditions that we've been on. But one of the important ones have been to the Arctic, where we're trying to understand mixing in that region and how changes in the freshwater budget from sea ice melt and land ice melt is influencing the structure of the upper ocean. So there are certainly expeditions there and more interest in the northern regions, because I think these are going to be some of the regions with some of the highest impacts. And I think the Arctic, especially, as you see in that map, it's not well sampled. Mm-hmm. In the oxygen map as well, it shows some pretty high oxygen losses, but the observational coverage is pretty sparse. So that's really one of our priorities, but it is also one of the most challenging places to make observations in. So it's gonna require a lot of dedicated efforts, more funding, and just more engagement from the policy community to understand that this is an important region for everyone. So I encourage you to go to scripps.ucsd.edu, our Scripps website, and look at the various expeditions that we have. And I think there's a couple that are in the Arctic region.
Oh, yeah. Yeah, I've seen some things about concerns with regard to oxygen in those regions as there's more freshwater input, then stronger, tell me if I'm getting this right, stronger stratification and less mixing of oxygen down into the water column. Is that the kind of trend we're seeing or expect to see?
So excellent question. So the ocean as a whole is expected to decline in its oxygen contents in a warming climate for two different processes. The first one is the relationship between gas solubility and temperature. A warmer water can just hold less gas, and colder water can hold more gas. So as we warm the ocean, the gas solubility of oxygen reduces, and it's able to hold less gas. The second process is what you mentioned about stratification. So a warmer ocean is also more stratified. And so in the high latitude, for example, in the Southern Ocean, in latitude where ventilation typically occurs in the North Pacific and the North Atlantic, ventilation is expected to weaken as the ocean warms at the surface. So there will be less transport of oxygen to depth through mixing and subduction than under a not anthropogenically warmed climate. In the Arctic, we have the additional complication of having Arctic sea ice. So we have now freshwater melts. So that the freshwater melt essentially leads to a change in salinity and density due to changes in freshwater content. And so that's going to impact the stratification of the upper ocean in that region. That might impact the amount of mixing. And I don't know how well the current models simulate oxygen distributions in the Arctic, but I think that's going to be a major opportunity for models moving forward as we try to explore that region. How will changes in Arctic sea ice impact the oxygen distribution in the upper ocean? That's going to be, I think, a major new insights from some of these biochemical Argo floats that can go below sea ice, and also these models that can resolve smaller scales that might give us more insights into these dynamics.
Oh, yeah. Well, very important area of observations. Yeah, another question, I think it's related. You've addressed it, how this can be applied, given to other parts of the world, and how can other parts of the world contribute to Argo? I guess, you know, part of that, you showed the map of all the different countries and most of the dots were green. And so what about smaller countries and how can they contribute to the Argo program?
I think all the countries can contribute. I think this is really why the COP is important and why scientists at the COP are critical players in this conversation, and why we're trying to reach out to the policymaker community about the importance of these measurements. Is that as we're starting to draft a Paris Treaty playbook or a roadmap for how we're going to address climate change, a critical part of how we're going to address climate change is going to be monitoring climate change, and specifically the ocean heat content. And so as countries are putting their nationally determined contribution together, their climate action plans, as countries are deciding on finance, on adaptation, on mitigation, it's really critical that we have the monitoring network in place to inform those decisions. And at the conference to parties, whether at the SUBSTA meetings or at plenary meetings or even in the hallways, I think one important contribution that scientists can have is to showcase the importance of these ocean observations to their national resources and their national adaptation plans, and to integrate their adaptation plans with these observing systems. And each country can, for example, contribute by deploying more Argo floats or making measurements regionally where Argo floats might not be able to make those measurements, for example, through gliders, through time series and moorings. The marginal seas are an important region. So places like Indonesia and the Mediterranean Sea, it's really important to have measurements that are not reached by Argo, but pretty much any country can contribute to the Argo Float program, and there's already a lot of them that are contributing. So I see over the 21st century that sustaining this program for a very long time, where all the nations are coming together and sustaining these measurements is going to be really critical. And the Conference to Parties and the UNFCCC is an ideal place to actually do that. And so I encourage anyone to go to the argo.ucsd.edu website and see how they can contribute. And also we're trying to reach out to everyone who's interested and try to showcase the importance of these measurements to our global community.
Mm-hmm. Now there's a sort of a related question is about these data. Are they open? Is it open data? And for example, could a scientist from Nigeria access these data that you are introducing to us?
Absolutely. All the data from Argo is processed and is made available to anyone. You can go to argo.ucsd.edu and essentially download.
I'm going to type that in.
Yes. And you can access that data and look at the various different products. And it's been used by scientists worldwide. It's also being integrated within models to provide ocean state estimates. And one of the priorities for the Argo program is to make that data available as soon as possible, quality controlled, and have that data being used by the global community is definitely a major priority for the program. Yeah, and one of the major successes of the program is its data accessibility.
Great. Let's see. Oh, another question is very interesting about the observations from Argo being very different from what we can get from satellites. So what about the maybe interplay or complementarity between satellite observations and Argo observations?
Great question. Satellites are absolutely critical, especially in giving us the spatial pattern of warming at very high resolution. We can actually see, now we can monitor sea surface temperature warming at very high resolution thanks to various NOAA, NASA, and ESA missions that are giving us unprecedented resolution of sea surface temperature change. But they can't really tell us about the structure of warming below the surface. Satellites also give us a great deal of insights on sea surface height change, and that's also an important component of the complementary between the Argo program and satellites. Sea surface height or sea level rise depends both on freshwater melt on land that is discharged, as well as the thermosteric expansion, so the expansion of water due to warming. And Argo Float essentially give us, by measuring ocean heat content at depth, they give us that thermosteric component. So they're really critical in informing what's driving the sea surface height changes that we've been observing in recent decades. So those two are really primarily the two complementary ways in which Argo is helping give a fuller idea of how warming is happening on a global scale. There's also a variety of other ways that Argo can help. For example, biochemical Argo, now that with these measurements in terms of nutrients or oxygen and carbon, they're giving us new insights on changes in ecosystem habitats or the carbon cycle. And for a long time, we've been looking at chlorophyll changes from satellites to infer changes in productivity. But our mechanistic understanding of what's driving productivity is still incomplete. So by having these three-dimensional structured observations of nutrients, of oxygen and carbon, we can actually use this subsurface data along with chlorophyll satellite data to try to understand what's driving change in productivity. I think that has applications beyond from climate change, for example, in informing fisheries models, or for informing changes in the amount of productivity in different regions. So both biogeochemical Argo, the Argo program, especially the deep Argo now that's going to measure ocean heat content changes below 2,000 meters. I think there's more and more complementary data that we're seeing both with satellites measurements as well as with other types of measurements. Atmospheric carbon dioxide measurements, for example, in terms of understanding the carbon flux between the ocean and the atmosphere. Oxygen measurements in the atmosphere and oxygen in the ocean. We can understand the exchange of oxygen between the ocean and the atmosphere. The list just goes on and on. There's no regrets with making observations, and they're absolutely critical to understanding how climate change is going to evolve in the future.
Oh, yeah. That's, I guess, can't be overemphasized. And I know here at Ocean Networks Canada, we're all about observations, and but sometimes we forget what the applications are for them, and you know how valuable they could be for understanding the changes. Let me just check, see if there are some more questions here. I actually had a question when you displayed your map of the. It was an animation showing the oxygen minimum zone extent at 200 meters, I thought that was. And the Indian Ocean on both sides of the Indian subcontinent was black, meaning zero oxygen or close to zero oxygen. And I wondered why that is, and because that really stood out on when I looked at it.
Yeah, so oxygen is low in the low latitude oceans, for example, the Indian Ocean, the Atlantic, and the Pacific, because there's not enough ventilation. So for example, in the tropical Pacific, the Pacific Ocean is ventilated from the high latitudes, where what we call isopycnals come up to the surface, and then they exchange with the atmosphere, and then they're subducted, and they go into what we call the thermocline, and that water is essentially ventilating the ocean's interior. However, there are regions that are what we call shadow zones, where some of that ventilated thermocline water just doesn't reach those regions. And so those regions tend to be ventilated by other processes like the equatorial undercurrents or equatorial jets that bring in oxygenated water from these different water masses through a different mechanism. And because ventilated waters don't reach the oxygen zones very much, they tend to be depleted in oxygen as consumption by microbes that consume organic carbon that descend from the surface over time. And so some of those waters end up being depleted in oxygen to a level that can be anoxic, where there's almost no oxygen. The Indian Ocean, these different oxygen minimum zones, the tropical Pacific, the Atlantic, and the Indian Oceans are very distinct from each other. The Indian Ocean, as you mentioned, has some of the lowest oxygen values. The tropical Pacific has some of the largest volumes of the anoxic oxygen in the world. The Atlantic, however, has some of it has oxygen minimum zones, but they're really moderate. And that's because the Atlantic is much more well ventilated than the Pacific Ocean or other basins. In the Indian Ocean, the oceanography there is quite different from the Atlantic and the tropical Pacific, where it's much more sensitive to monsoons and to coastal currents and eddies that are still actually not very well understood. There's been some papers by a colleague, Laure Resplendy, that have used high-resolution models to try to understand what drives the oxygen minimum zone distribution in that region. And it turns out that eddies and Kelvin waves and these sort of regional scale, 10 kilometer to 100 kilometer scale processes are really important in setting the distribution in that region. So that's generally really the different processes that are governing oxygen minimum zones in these different regions. And it also highlights the importance of making measurements in that region, because we ought to understand the mechanisms driving, for example, why is the tropical Pacific more oxygen depleted than the Atlantic, and what is the role of these new processes? Things that we find fascinating, but are really important to understanding how ecosystems are changing in that region. Yeah.
Right, yeah. Right. One other thought that popped into my head, you were showing the flooding on the beach of San Diego, so using models to be able to predict this. And what came into my head was the flooding in Venice. And if there are similar models that are helping people to predict the high tides and the flooding that will happen in Venice and places like that.
I am not an expert on sea level flooding models. However, I believe that there's quite a few out there. There's wave forecast models and a variety of different models that help us understand how sea level is changing, both to high wave events and king tide events, for example, and long-term sea level rise. For Venice, I'm not really familiar with the geography or the oceanography in that region. And I don't know. I don't know what really sets the sea level in Venice, but it's a good question. Maybe we should look into it. I think we could probably use, I think the rest of the team would be really happy to go and make some measurements in Italy and enjoy the food. But I think it highlights the importance of making these observations and improving our model understanding of what causes these flooding events, especially in regions like Venice, where the cultural heritage is enormous. But I believe there's quite a bit of studies happening in Venice at the moment. There's a lot of attention on it. But we ought to remember that other communities are also just as equally important, especially small island nations that may not have the same resources. And that's something we hope to address in the near future, is having the right observational coverage and model understanding to try to help communities and also partner up with communities, and not help communities, but work with the communities to try to get a better insights into what's causing flooding events in different regions, especially in the western, the South Tropical Pacific. And that's going to require policymakers to really work closely with scientists. And that's a challenging but highly rewarding process.
Yeah, I was just reading about an example of that in the Marshall Islands. I think it was a story in the Los Angeles Times about one of the atolls, Bikini Atoll, or I can't remember the name of it, that was used for nuclear testing. On this particular location, a large amount of radioactive material was covered up in concrete and what they call the tomb. And now as sea level is rising, it's becoming unstable. And it moves up and down with the tides. And that's something they probably didn't think of when they were building this structure 40, 50 years ago.
That's an interesting point. I think we're now at a point where with these new measurements and with how our population is changing globally, our population is increasing, we're realizing that even just with a variable climate, we're really increasingly dependent on our environment. We're increasingly dependent on our knowledge of how our environment changes, both in the short term and on very long term. And I think that's one example of the various things that we didn't expect 10 or 20 or 50 years ago. And it highlights the importance of being proactive about how we use our environment and our place within it. And as Roger Revelle once said, to better use our environment, we have to understand our environment. And I think it really highlights the importance of sort of this understanding how our climate is changing and monitoring and observations, their roles for improving models, and also their critical role in informing mitigation, adaptation, and impact. So I think your question is absolutely on point, and I hope the community in Madrid sort of converges more along those points. And I think it's moving in such a positive way. I've attended COP since Doha in 2012, Qatar, and I've attended the Warsaw meeting and the COP in Paris, where the Paris Treaty was signed, and in Poland again, and in Marrakesh. And I've seen over the years how the community has been changing in such a positive light and trying to address more of the ocean impacts. Back in 2012, there was absolutely no mention of the ocean. There was possibly one event on the oceans. I was one of very few ocean scientists. Fast forward 6 years later, we're calling the entire COP a blue COP. And I think it shows the importance of having scientists at these meetings and having committed scientists engaging with policymakers and sort of moving our community forward. So it's a really exciting time to be engaging with this community.
Well, thank you for your sense of enthusiasm and excitement and optimism, which sometimes we forget about that, but it's very important. And I really appreciate everything that you've presented today. I think we've actually gone over the end of your segment, but if people have questions, they can still send them in and we will try to answer them. And beyond this, your segment is going to be recorded along with all the other segments, or has been recorded. And so that will be made available online on the Virtual Blue COP 25 YouTube channel, so people can be able to watch this at a future time. But thank you once again, Yassir, for your very interesting presentation today. And we hope to hear more from you in the future and from Scripps Oceanography, and as we sort out these puzzles and find our way to a bright and optimistic future. Thank you very much.
Thank you very, very much, Dwight. And thanks again to the Virtual Blue COP team. This has been a highly inspiring event. Thank you so much for pushing the COP into a carbon neutral direction, I hope. So thanks everyone again.